Hi, this is Paul Gregg, and I think this is the fourth and last video of my series on spaghetti material properties testing in support of the design and testing of spaghetti towers. And so, let's see. Joint tests. We've covered so far a bunch of buckling tests, and buckling seems to be, the most critical thing in a spaghetti tower, and so that's where I've concentrated. The spaghetti tower is required to be 12 inches high at the platform for the weights and at least 16 inches high total, but the length of spaghettis are only 10 inches. And so at some point you're going to have to splice spaghetti pieces together. And we'll see how to do that. I came up with four simple methods. You just do a single lap joint that's bonded on only one side with hot glue, or this type two, I call it, single lap joint that's bonded on both sides. Just spread glue along one side. And one variable in this whole thing is how far you lap these things. And obviously, the more you lap it, the better it is, but the more heavier it is. And maybe you don't need to lap it too much. And if this was a real building or an airplane, we'd be really trying to get the details out here and get the last tiny bit of weight out of it. But this doesn't matter too much. It's a longer lap is not that big a deal in spaghetti towers. But in real engineering, you want to use as little as material and cost as possible. Um, Type three, the butt lap joint. You cut off a little piece of spaghetti and lay it on the side and then bond the whole thing on one side. Type four is a double butt lap joint where you have two pieces of spaghetti. And I guess I uh, I made these. Oh, this is the test. Just push on it until it breaks. Take note of the load. And as long as that load is well above the a buckling load of the stuff anyway, what I was going to do was, oh, well, I guess I can't. I made a bunch of these little lap joints and that they're just how it showed on the diagram. Okay, this is the testing results. Tested a bunch of type ones, type twos, type threes, and type fours with different lap lengths, okay, in millimeters. And then I saw how much load they would take using that test method. And it went pretty fast. So that's the load in grams, and that's for reference the load in newtons. Um, Okay, so the ones I deemed kind of an acceptable range were the red ones, where the lap was big enough that it worked pretty good, and I thought, well, these down here they're not very good, and so it's easy enough to make a decent lap joint, at least bonded on both sides, and probably a double lap joint. Just stay with the double lap joint; they're not that heavy, and bonded on both sides. Those got very good. Those carried very good loads. You can see here above 8,000 grams, which is 8 kilograms. Um, yeah, so that's well above what these things are going to fail at in any other mode. And so if you just make the lap length, um, you know, above 25 millimeters, above an inch, about a half inch on either side, then it seems to be a really good joint. And that would be a general rule going forward. Just do a double lap joint wherever you have it, wherever you want longer than a 10-inch piece. And uh, and then we move on to three-point bend testing. This is one way of comparing materials and getting some data out of it, although it's a little cloudy because it's not pure bending, it's not pure tension, it's not pure compression, it's not pure shear. It's a test that kind of has a mix of things in it, and we'll look at that. This is the little wooden test fixture I designed. This is the postal scale that goes up to 70 pounds. And then you just put a piece of spaghetti in there. You can vary the total length of the piece when it's being bent, and you just put it in the center of that and push down and record how much load it takes to break that piece of spaghetti. Of course, the longer the length, the easier it is the longer the length of the spaghetti, which is the purple piece here, the easier it is, the less force it takes to push that down. I'll go through a little bit about what's going on here. This is what we call and it's really an introduction to the shear and moment diagrams of a beam. When we analyze beams, this is a 3-point test beam and this is a 4-point test beam. The 3-point test beam is used if you really make it short, then the shear dominates it and you can get a pretty good shear number. Um, and if you use a 4-point bend test, the nice thing about that is between the two load points, the moment is, this is the shear diagram, this is the moment diagram down here. The moment's constant across there. And so sometimes we use that. I only did the 3-point bend test, and it's really just to compare the kinds of spaghetti and maybe look and see if well, just yeah, it's not as good at data as tension and compression as far as engineering goes, but it can be used for acceptance. If you were gonna, if you're really interested in, this is what we do for aluminum and steel and composites. You test when you get a batch of material from a supplier, uh, you test you test some of it, yeah, at some frequency so that you know that the batch out of the factory is good. If I was interested in the strength of dry spaghetti, I would every box of spaghetti, I'd pull one out and do the bend test, and I'd have some criteria that okay, this is strong enough spaghetti. They didn't make it thinner diameter at the factory or whatever. And we don't really care much about that, but that'd be the equivalent of what you do whenever you want to accept material from a supplier, is to test it to make sure their process specifications are making it consistent. So I won't go into much detail about the shear and moment diagrams. Basically, there's the shear is on one side is the negative of the shear on the other side, and the moment peaks in the middle, which is what you'd expect. It's going to break in the middle, so the moment peaks in the middle. Anyway, this is kind of how this works. So we have some kind of a beam. In our case, the spaghetti. This is a square piece. The top of the piece, when you do bending, when you push in the middle and you hold it on the sides, it goes into a bending. It makes a smile if you're pushing down. And the top layers of that material are in compression. The bottom layers are in tension. Okay. And if you want to know the stress from a bend test, there's a pretty simple formula. The stress is equal to the moment, which is the length times the force on one side, times the y, which is d over 2. It's halfway in there, and then divided by the moment of inertia. And we've talked about moment of inertia, area moment of inertia. And this is kind of a diagram. The stress peaks in compression on top. It peaks in tension on the bottom. And right at the neutral axis, there isn't any compression or tension. And you get kind of a feel for that. That's just an introductory to beam analysis. So this is what I did. I put different lengths of spaghetti in there, 4 inches, 3 inches, 2 inches. Um, and this is for the thicker tubular spaghetti. And then I loaded it up to some number of grams. And when it broke, I wrote that down and convert that to pounds. And then I did the formula, moment times this distance to the neutral axis divided by the moment inertia, which was easy I already knew those things. And I came up with a stress that's similar to tension stress, okay? And I took the averages and the deviation. So I'm getting pretty consistent numbers here with the better goods. This is the American Beauty, the thinner spaghetti that's solid. And I got a lot lower loads, but when you do the math, you calculate a similar stress, and they're in the range of the other thing. And this is the Berea, the other thin, solid spaghetti, and I got similar numbers there too. So this is the test. It's a little hard to see. I'm pushing down on that big stick on the top and the spaghetti's, and then I'm looking at the thing. So I start pushing down. I look and see where it peaks out. Right when it snaps, I'm at a certain load, and I write that load down. So this is like a 4-inch span, and I broke the spaghetti in there. So that was the testing, and I got pretty good correlation to the what would be the tension strength of spaghetti with the 3-point bend test. So now this is all of those results combined. The Better Goods, the American Beauty, and the Berea. What I'm doing here is trying to back out the modulus. Okay, this is a little tricky. I know this equation, but if I knew the length, I knew the moment of inertia, I knew the load it broke at, I should be able to turn that equation around, solve for E, and back out the modulus of elasticity, and that's what I did. So with the Better Goods, I backed out 500,000 psi. With the American Beauty, 800,000, and the Berea, 667,000. That's not dissimilar to what was published in this uh, Guinea Rio Rojo uh, testing, where they tested dry spaghetti. And so my stiffness is about the same. Um, okay, I think I'm about done. I was going to use a different system for testing tension that was more complicated. I didn't do that. This is that what I saw earlier. And the only other thing I'll say, I'll put a link to this. This is a PowerPoint by I'm not sure who it's from, but it's a design and construction of a spaghetti bridge, which is different than our spaghetti towers, but there's a lot of great information in that. And I'll put a link to that in there. Um, this John Hopkins University, and they go through a really nice presentation of making uh, bridges, and that can be another contest you want to do. So they talk about trusses and things like that. And anyway, so that's all I'm going to talk about today. Um, Thanks.